to today's class on practical physics. We want to look into experiment on rectangular block prism. We have posted a video on rectangular block prism. That is the first part of it. I want to see another part of a rectangular block prism experiment to discuss. Welcome guys to today's class on practical physics. In this video, we want to discuss experiment on rectangular block prism. We have posted the first part of it. This is the second part of rectangular block prism, where we have a radius, a circle, and all have you on the experiment. So we want to see how we can perform this experiment without touching apparatus. And that means we want to use formula method to appreciate it, so that if you are given such experiment where there is no light or where there is darkness, you will be able to perform it because you know the formula method. Now, first thing to note, why using formula method to solve any question on experiment or to perform experiment on any aspect of practical physics, what you do is, for this question now, we have to note what our refractive index means. Yes, you know, it's coming from light. This light ray is coming from air and it's entering the glass and going. So refraction tends to exist because there is change of medium from air to glass to air. So from air to glass, it will reflect toward the normal, then to air, it will reflect away from the normal. This is the pin. This is the traces of the light ray. Yes, light ray, it's moving this way. That is the direction of the light ray. This is rectangular block prism. And look at a circle made on it with a radius. Now, what we do first is that we have to recall Snell's law, which says that the refractive index is sine I all over sine R. We have to note this. We have to also recall our SOHCAHTOA. SOHCAHTOA, that is sine equal to opposite over hypotenuse cos, adjacent over hypotenuse tan, opposite over adjacent. We have to recall that. Now, what we have to do is, first, get this diagram out, bring it out. That means this is my radius, this is my A, this is my perpendicular line. So this is my A, my R, and my I. Then the next one is to bring out this. So this is your R. That is, at this point, this is your refraction. This is your radius, this is your radius, then this is your B. Now, the implication is that this is your radius because we say radius is the distance from the center of a circle to any point on the circumference. From the center to any point. So they will have the same word, radius. But their A and B will not vary, and their I and their R, that is the angle of refraction, will not vary. So for here, it means that the R will be constant, but the I and R will not be constant, and the A and B will not be constant. So for this part, the formula we use is, we are looking for A, and we have opposite, we have hypotenuse, we have angle. We say sine I is equals to what? Opposite over hypotenuse, A over R. Therefore, A, which you are looking for, equal to R sine I. That is the formula we'll be using for this. We say A equal to R sine I. Then for this one, this is B, this is R. So we now say sine angle of refraction is equal to opposite over hypotenuse. Therefore, B will be equal to capital R sine R. So B equal to capital R sine R. So that is the formula we are to use and put it here. After noting this, your formulas you have to use to get your A and your B. Next thing to note is that the refractive index has a range. The range begins from 1.46 to what? 1.54. So that means if we finish solving, we'll still fall at this. But before then, we need to pick a value here that we are to use so that we can put it in the calculation. Now, I can pick 1.48. 1.48 falls inside here. Why I am picking this value is we need to know the value of R because we need R here. So that means from here, we say that sine R is equal to sine I all over refractive index. Therefore, R will be equal to sine inverse bracket sine I over refractive index. So we have another formula, R equal to sine inverse bracket sine I over refractive index. So these are the three formulas we need for this experiment to be performed without touching apparatus. Let's see how to make it. So let's get our A first. Now this is the refractive index we are using. Refractive index is equal to 1.48. Radius is equal to 5 cm. So we'll be using capital R to be 5 cm. You can put any radius you want. You can use 1, 2, 3, 4, 5, 6, 7, any number you want. But that number will be unique. You will use it throughout. So, having noted that, now to get our A, we say R is 5 sine what? I is 30, that is the first value. 5 sine 30, that is 2.50. 5 sine 40, 3.21. 5 sine 50, 3.83. 5 sine 60, 4.33. 5 sine 70, 4.70 approximately. That is to 2 decimal places. Now, before you get your B, you need to know what your R is. Your R will be equal to, for the first one, equals to R is equal to sine inverse bracket sine I over sine 30 over 1.48. Because you say let the refractive index be 1.48. So we now say shift sine bracket sine 30 divided by 1.48. So we'll be having individual value of R. The first one to be 19.75. Let's see the second one. This is for 30, the first one. For the second one, We change 30 to 40. 25.74. We change 40 to 50. 31.17. We change 50 to 60. 35.81. We change 60 to 70. 39.41. So these are the values of your angle of refraction. These are the value. We will now put it here. For the first one, R sin R, that is 5 sin 19.75. We have our B to be 1.69. 5 sin 25.74. 2.17 sin 31.17. 2.59. 5 sin 35.81. 2.93. 5 sin 39.41. 3.17. So we have gotten our answer. Look at the values we use to get it. We have gotten our A, our B, our I, our R, everything. Remember that the radius we use depends on what you want to use. That is about how to make your table. In the next video, you will see how we can plot the graph of A against B, get the slope, get the error in the slope, and state what physical quantity A represents.